Okay. Well, actually, you can see from here that if you look at the slope, right, of a line, as I said before, we also call it, it's a rate of change. It's the rate of change at which of the function f. Now, you might be thinking, why is it called that? Well, the idea is this. Let's see if I can get to that. Here we go. So the idea here is really what I'm trying to show you here. If you were to increase a linear function, or a straight line, if you were to increase the value by 1 unit, increase meaning x, so if you increase x by 1 unit, whatever that unit is, it depends what x is, your y value will change by m units. I mean, you can show it direct by calculation, but if you increase x by a unit, your output is going to change by m units. It might increase, it might decrease, but that's really why it's called the rate of change. And that's really the significance of the slope. Okay, so that's all fun. Now let's do an example. So let's consider this function, 4 times x minus 8. Okay? So what we want to do is basically confirm that the rate of change is 4. In other words, we want to confirm the slope is 4. Okay? I mean, you could probably tell just by looking at it if you think about the mx plus b, but let's actually do some calculations. So to get the rate of change, the slope, we need 2 different points on the line. So here's our first one. When x is 0, we can get f of 0, right? Which is, of course, 4 times 0 minus 8. So I'm calculating, so I have 1 point here. The 0 I chose arbitrarily. I could choose any point I want. But this is 1 point on the line. If I replace x by 0, I get the corresponding y value from the formula. And here's another point. Again, these 2 numbers I chose randomly. I could do 0 and 1, which I do here, right? We're getting f of 1. So we get our points. But I could have chosen 1 and -5, 2 and 8, 2 and 6, I mean. I could choose any 2 numbers I want for x. Then, going back to that slope formula, this is just really confirming it, right? You have change in y over corresponding change in x. I think they call it rise over run. I think some people call it that. But that's all I'm doing here. Change in y over corresponding change in x. Change in y, change in x. See? And we see that, yeah, the slope, the rate of change is 4. But notice also, again, that by increasing x by 1 unit from 0 to 1, we can see that the y value increased by 4. It went from -8 to -4. Okay, that's good. But just to illustrate what I'm saying is, let's use 2 different points. So again, we're really just calculating slope, which is the same as rate of change. I'm also illustrating, no, I'm good. Okay, so that's what's happening here. So again, same idea, right? We get 2 different points. When x is -1, right? We get -12, okay? That's just by direct calculation. We get 2, okay? Our output is f of 2, which turns out to be 0. So let's get the slope. Let's get the rate of change. And we get 4. Okay, good. So that's what we get. Okay. So we end up with that. All right, cool, cool. All right, so that's what we get here. So that's the slope. Okay. So that's just an example that we're dealing with. Now, this was so much fun. We can actually get in the equation of a line through 2 points. Again, linear functions are just non-vertical lines. So let's find the equation of a line through these 2 points. So if we want to do that, remember, we need the slope, and we can use either point. So either way, we have to get the slope. So this is what I'm doing here. change in y over corresponding change in x, as you can see. Right? Again, we're just dealing with linear functions, which are non-vertical lines. Okay. So we get the slope, right? And now we have our slope, and we're basically done. We just need to write an equation of the line. Well, this is 1. Basically, what I'm doing is I'm using that point slope form from before, where I'm using this point, 3, 7. You know, it was on the earlier slide. We have y minus the y coordinate is the slope times x, the x coordinate. If instead I used this point, I would have this. Again, I'm using that point slope form from before. That's all I'm using. Now you're probably thinking, can't we just do the y equals mx plus b? Can't we just use that form? Well, yeah, we actually could. We got our m is 2, but we have to figure out what b is. That's easy to do, though. I mean, essentially, you just use either point and solve for b. You know, since these points are on the line, they have to satisfy this equation. Since the points are on the line, they have to satisfy this equation. So because of that, we can use either point, like so. So I'm using the first point, and now we can figure out what b is. And then you just solve algebraically for b, right? That's all I'm doing. Subtract 2 from each side, right? Because we have 3 equals 2 plus b. 2 times 1 is 2. Subtract 2, so we get b is 1. And so we have our line, right? Y equals 2x plus 1. So we have a linear function here. You know, we have y equals 2x plus 1. Y is the output, x is the input. And notice our function is increasing. I mean, we kind of saw that already because we had that idea over here, right? And from before. Actually, no, okay. But anyway, from the graph, we can see that the function is increasing. Right? Because again, as you move to the right, this line goes up. Going up. Okay? And you can see, oh wait, it's not, well, it's kind of hard to see from this graph, but the slope is 2. So the rate of change is 2. Remember, slope and rate of change are the same thing for linear functions. Okay. And this is just saying what I said before, that in general, this is what I was trying to illustrate with this example, but if you want to know if a linear function or a line is increasing, decreasing, or constant, you don't have to graph it. You could just find the slope. That is, you could find the rate of change. Okay? And you could just do this. You know, it depends on what the slope, the rate of change does. If it's positive, then it's increasing. If it's negative, then it's decreasing. And if it's 0, it's constant. So that's why linear functions, that's one of the reasons linear functions are really nice. So, okay, I guess we can stop here. So, okay, I had some more examples, but I guess why don't we start with those examples next time. So I guess what I'll do now is we'll stop here. Okay, let me stop the recording.